Questions? Where was I? All right, so now let's talk about sinusoids and complex exponentials and ways that we could use that information. The main thing that we want to get comfortable with is playing and talking about time domain and frequency domain. Sometimes it's nice to see the time domain waveform, and sometimes you want to just know what's the frequency content, or what do I really have going on here. This just is allowing us different ways to see or think of or visualize or viewing these signals. Meaning, if you now have a filter design problem, it might be nice to know the frequency content and not this time domain picture. You might say, I can't tell what the frequency is in the time domain. It's going up and down a lot. But if you now look at it in the frequency domain, you know exactly what frequency you have in terms of the frequency content. And you should already be very comfortable with this idea. We've already talked about, and you've played with the sines and cosines a lot already. We're in the time domain. You've looked at phasors before, meaning if I give you a cosine or a sine, you can give me the magnitude and the angle of that. And that's really allowing us to then go into this frequency domain description. For example, if you start with x of t and it's a cosine omega t plus theta, what's the phasor form of that look like? Bless you. That's just a at an angle of theta. Now, you have to realize that you're at the restaurant. Meaning you want to make sure that you have, may I have my dressing on the side, please? Well, now you need to know what the frequency was. If somebody says, oh, the magnitude is A and the angle is theta, you need to know what the frequency is in order to really capture what's going on. So that omega is somewhere on your page or in your head. You know what the frequency is. The phasor form just gives you the magnitude and the angle. You really need to keep that omega on the side. You need to know what the frequency is. Now, that's the phasor form. We can now use our friend who might be at the table next to ours at the restaurant, only via time travel, so that would be some non-causal relationship maybe, but we're trying to tell stories here, right? Because you learn better by stories. What's Euler tell us? Euler gives us this relationship between complex exponentials and sines and cosines. Meaning, if you now wanted a cosine of omega t plus theta, and let me go ahead and make that a specific frequency, not a bunch of frequencies omega. Let's just fix it as omega naught. I could work with that by playing with this complex exponential and then at the end just taking the real part of that. Meaning I can now say that's a e to the j omega naught t plus theta, the real part. And what we're going to be doing is thinking about this AE, because actually these complex exponentials are much easier to play with than sines and cosines. We now want to be able to play with this complex exponential, and you could just think of this as a rotating phasor. It's rotating at a frequency of omega naught. Time is just clicking away, so now you have omega naught. That's this spinning thing in the complex S-plane. It has a length of a, and if you took a snapshot at t equals 0, it would have been at an angle theta at that instant of time. That's a way to think of this complex exponential. So now we're just going to say, let's just recall these rotating phasors. So that we now have this real part, the imaginary part, and the phasor has a length of a, and this is going around defined by this omega sub naught t plus theta. If we want the projection onto the real axis, that's actually going to give us the a cosine omega naught t plus theta. So we're just now having this phasor spinning around, and we're simply concentrating on what's being projected onto the real axis, and that's what's giving us our a cosine of omega naught t. Now, we can actually capture this information other than just this complex S-plane. We can capture this in a line spectra. What do we need to capture? It'd be nice to know the magnitude, the amplitude. It would be nice to know this angle, and it would be nice to know omega naught. Well, our line spectra allows us to do that with just two plots, so it's sort of like the Bode plot. We're looking at magnitude and angle information. And this will be called, like I said in Chapter 6, we'll be playing more with this, but you can now understand what's going on with this single-sided line spectra. And the way that we will do it is we will have an amplitude piece. Here's the axis omega. We had a particular frequency, omega naught, and at that frequency we had a specific amplitude A. That's now the magnitude content, or the spectral content in terms of the magnitude. We can also, right underneath that, if we're consistent and sketching this properly, we can now look at the phase content. The frequency is already captured at omega naught, but the angle now is this angle, let's call it theta. And that now, if I give you this picture, you can tell me, oh, your cosine is A, it has an amplitude of A. Cosine, the frequency is omega naught, so that's omega naught t, and the angle was theta. The argument then of that cosine is omega naught t plus theta. And this is another way of viewing that. Now, if you had several different sinusoids, they would each have their own spectral line. And now you can start thinking about, oh, what if I didn't want that frequency, but I wanted these frequencies? How would I filter that? You now have a picture of what you might want to do. These are the signals, and now the system, via its Bode plot, tells you how it's going to shape these signals as these signals are processed through that system. Now there's another line spectra. This is the single-sided line spectra. There's actually a double-sided or a two-sided line spectra. So let's look at that one. And how it comes into play is actually using the same rotating phasors, but now we have two phasors. One's going counterclockwise, the other one's going clockwise. They're in sync. They're rotating exactly opposite to each other, and we're just going to add their pieces up. Meaning, we could now have a piece that was, let's say, a over 2, and maybe this one is now the omega naught t plus theta, but we now also have another one that's spinning clockwise, and that's now with a negative sign associated with it, and it also has a magnitude of a over 2. So that if I now project this one and I project the other one down, now I'm going to really have this piece, this a cosine of this angle here. So the projection, or what I really am doing, I now have this a over 2 e to the j omega naught t plus theta plus an a over 2 e to the minus j omega naught t plus theta. And what is that? That's our cosine, isn't it? But you can now sketch that in this frequency domain sketch as a two-sided line spectra. And where are those lines going to be? Now we have two lines. Now we have a positive frequency and a negative frequency, and we get the negative frequency because of mathematical simplification. It helps us. So the fact that we have a negative frequency at -7, who cares? We have a frequency of 7 radians per second. That's just going to be the nature of the beast. Now we have this two-sided line spectra. We have something at omega naught, and we have its buddy at minus omega naught, except now in the two-sided spectra, the amplitudes are half of what they were in the one-sided, because we're combining these together. And so this is now the amplitude. And what about the phase? We have information at both of those frequencies. It's the same frequency, just the negative of 1, and I put those maybe exactly in the wrong place, but that's okay. This one, let's say, is now theta. I'm going to have to move this one. And this one now is minus theta. Our angle has odd symmetry. Our magnitude has even symmetry with respect to DC, or 0. And this is just another way of thinking about the frequency content of sines and cosines. Now, how do we, here's something maybe for homework help if you're still kind of scratching your head about Euler. What if we wanted to turn a sine into a cosine? Using Euler. What do we know? We know that the sine of x is this e to the jx minus e to the minus jx over 2j. And we also know that the cosine, let me just say, of y is this e to the jy plus e to the minus jy over 2. And we want to go from blue to black. Notice I didn't say black and blue. You won't be that beat up after doing this, but those are the colors right now. So we're black and blue over this Euler expression, but there's a couple of observations that we can make in this conversion. One is that j, this square root of -1, is e to the j pi over 2. If you simply look at what you have in the complex S-plane, if we wanted j, that's also this length of 1 at an angle of pi over 2. The other observation is that -1 is e to the j pi. So if we're again looking in the S-plane, we want to go over here to -1. Well, that's the same as taking a magnitude of 1 through an angle of pi. So using those in my sine expression, I'm going to try to come up with a cosine. If I start with sine, that was e to the jx minus e to the minus jx over 2j. Let me use my two observations. I can now say that that's e to the jx. I haven't changed anything, but now let me rewrite that -1. So now that -1 is going to become an e to the j pi. And I still have an e to the minus jx. But I also want to change that j because cosine didn't have a j downstairs, but I can write that as e to the j pi over 2. We okay with what I've done? I just plugged in some complex exponentials in some judicious locations. If I'm dividing by e to the j pi over 2, that's like multiplying by e to the minus j pi over 2. Or I could multiply by 1. I could multiply the numerator by e to the minus j pi over 2 and the denominator by e to the minus j pi over 2. So this denominator complex exponential is gone. I can now rewrite this as e to the jx, e to the minus j pi over 2, plus e to the j pi, e to the minus jx, e to the minus j pi over 2, all over 2. All I've done is multiply by 1, and that's a legitimate operation. Now let me combine my exponents. E to the j, and this is now x minus pi over 2, plus e to the minus j x, and what do I have left over? If I look at what I have over here, I have j to the pi over 2. But I can write that as minus a minus pi over 2, and so now I can say x minus pi over 2. And this is over 2. But what is staring me in the face? That's a way of relating the sine to the cosine. This is now equal to what I started with, which is the sine of x. And so if you forget these trigonometric relationships, you're not going to forget Euler. You can derive these trigonometric relationships. And this is how you can now start to relate. When you're adding up sines and cosines, you can now start to add those up. Another way of viewing this is to say, oh, if I had something that was a cosine, here might be my cosine axis, and here is my positive sine axis, meaning what did we just see? We saw that sine of x, which is, let's say, right here, is equivalent to cosine of this angle, which in the sine direction is 0, minus 90. So that's the same as the cosine here of x minus pi over 2. So if we had two pieces, a sine and a cosine piece, if we had a cosine piece up here at some angle, let's say 30 degrees, and we had a sine piece at a different magnitude, but, ooh, that was a jerky angle, but this is now, let's say, 45 degrees. We could vectorially combine those, and as long as we write those in terms of this axis, with that being negative, we'd have the cosine expression. Something to think about. But this is a way to sort of quickly start to get the connection between sines and cosines. And I don't know where we'll pick up on Tuesday, but stay tuned.